Looking at conditions that would cause a elimination to proceed through an E1 versus an E2 mechanism. So let's do E2 first. So just kind of a reminder, remember these were our second order reactions, right? Our rate law involves both the alkyl halide and that base. So because the base is involved in my rate determining step, the identity of that base is going to be important. If you remember the rate law for an E1 reaction, the base is not part of my rate law, so the identity of the base is not as important. So here, a better base is going to give me a faster reaction, that sort of thing. I am just going to do a quick mechanism for us, just so as we go through things, we can kind of remember what's going on. So I'm going to draw that proton. And then remember, from a stereochemistry standpoint, because this is all happening at the same time, I do need to make sure that that halogen and the hydrogen are anti in the same plane, so anti-coplanar, anti-periplanar. So I do want to draw some good stereochemistry on this, or at least an attempt at it. So this time I had two R groups on there, so those are both methyl groups, and then I had my hydrogen. And then I'm just going to use B for base. And the base is going to take the proton at the same time that those electrons go down to form that pi bond at the same time that my leaving group leaves. Because it's concerted, I do want you to draw the transition state. So I'm going to focus on the two carbons where the new pi bond is forming, right? Where all the action's happening. So I'm breaking the bond between the carbon and the hydrogen, forming the bond between the hydrogen and my base, forming my pi bond, and breaking the bond between the carbon and my leaving group. And everything else is still here. And then my transition state notation, and then my product. So it's kind of messy, but I do have that, right? There is a hydrogen here. You don't have to draw it, but there is one still there. We do follow Zaysev's rule. Remember, that was the one that said that if we have different ways we can draw our alkene, right? If there's different possible products, then the major product is the more substituted product. So we did have possibilities. I don't know if you guys see that. Let me draw it without all the stereochemistry on this one. Sorry, that's really ugly, but I have a hydrogen here, right? Those are the ones that we took, but there are hydrogens on those carbons also. So it was possible to do something that's really, really messy. It is possible to do something like that, which is the same as doing it that, but those are possible products. These would be our minor products. The one up top here, I'm going to take that off just so it looks more normal when we draw a skeletal structure. This one here is my major product. So anti-coplanar, anti-periplanar geometry, and then Zaysev's rule. I didn't draw an energy diagram, right? That energy profile diagram when we did this before, but it would look very similar to our energy diagram for an SN2, right? It just takes in one step, place in one step. So we're going to go up to our transition state and then down to our products. So my reactants, my transition state, my product. If we were to add some energies in here, this energy difference is my activation energy. And then this one, either delta G, Gibbs free energy change, or delta H, assuming that there's only heat transfer going on. That would work also. So some of the specifics for this one are base. Because the base is involved in my rate determining step, the strength of that base is going to affect the rate. So the rate of an E2 mechanism increases with increasing base strength. So the stronger the base, the faster an E2 reaction. That's going to be one of the things, if you have a strong base and you're picking between mechanisms, E2. E2 is the one that involves that strong base. If you have a strong base, that base really wants a proton, so let the base be a base, have it take a proton, you have an E2 mechanism. The leaving group, and this is going to be true for all of our different mechanisms, the leaving group is involved in our rate determining step, so the rate is going to increase with a better leaving group. So rate increases with a better leaving group. And it's the same trend that we saw in chapter 7, right? Better leaving groups were weaker bases, right? Instead of them donating electrons, they want to take electrons and leave. So same trend that we've seen before. The solvent, honestly, for an E2 mechanism, a variety of different solvents work. I actually learned it with a polar aprotic solvent, but a protic solvent also works. It can actually do both. The aprotic solvent would, a protic solvent would stabilize that base, but if the base is strong enough, it doesn't really matter. So a variety of solvents work. Again, I learned with aprotic, polar aprotic, but protic would be fine also. So just know that a variety work. The substrate. So the substrate being my alkyl halide. I might not have referred to it as a substrate before. If you're talking about SN1 and SN2 reactions, the alkyl halide can be your substrate also. The substrate is just kind of the generic way of saying my main organic reactant. We are going to be doing substitution and elimination reactions with different functional groups yet this semester. So it could be that the substrate is an alcohol in chapter 9, that sort of thing. So the alkyl halide for now, but just so we can extend it to other functional groups, we can say the substrate. And for this one, the trend is actually going to be opposite to what we saw with SN2. With SN2, tertiary alkyl halides were too sterically strained for the nucleophile to fit into that partial positive carbon. Here, because it's an elimination, right? My base is grabbing that proton that's kind of hanging off on the side. It still works. Tertiary is actually going to be faster. So the transition state, in the transition state for this one, the alkene is partially formed. So better substitution actually stabilizes that transition state. You can say the transition state kind of looks like the product, and the product is more stable if it's more substituted. So having the transition state also more substituted is going to stabilize it. So this is an opposite trend to what we saw with SN2. So watch out for that. A lot of times folks will think that the SN2 stuff is the same for the E2 stuff, and it's not true. This is the opposite to the trend seen with SN2. So just be careful. Don't assume that because there's a 2 in the title that they're the same. This one isn't. E1. E1 were our first order reactions, right? This time my rate law only involves an alkyl halide. It doesn't involve my base. This one takes place in a two-step, where the first step is my rate determining step. So again, a quick reminder of our mechanism. So I'm just using X as time for a generic halogen. So my leaving group leaves. We go through a carbocation intermediate. Because of that, watch for rearrangements. I do need to draw hydrogen. Base. So the base takes the proton, and the electrons between the proton and the carbon go down to make my pi bond. And then we are following Zaitsev's rule, which is why we took that proton and not one of the ones on the other adjacent carbons. So this is my major product. We would have the same minor product that we had with the E2 reaction, so follow Zaitsev's rule. Carbocation, again, watch for rearrangements. Or resonance. If you can make that carbocation intermediate more stable, you're going to do that. Energy diagram for this is going to look very similar to an SN1. Right, we go up, we dip down to that intermediate, we go back up, and then down to our products. So reactants, my first transition state, my carbocation intermediate, my second transition state, and then my products. The activation energy of my first step is bigger, right? EA1 is bigger than the activation energy of my second step, meaning that my first step is slower than my second step, right? My first step is my rate determining step. It's the slowest step in that mechanism. And then my overall energy change, either delta G or delta H, whichever you want to use. So for this one, the base, the strength of the base does not affect the rate. Right, if we go up and look at that mechanism again, my base, right here, doesn't show up until that second step. The first step is my rate determining step. My second step isn't. So since the base is not part of my rate determining step, the strength of that base is not going to affect my rate. So for that reason, it does not have to be strong. If you have a strong base, E2. If it's not that strong of a base, now we have to consider SN1 and E1. So weaker bases are okay. So something like water, alcohols, these guys are going to favor E1 versus E2. We'll throw a substitution in later. The leaving group, the same as with all of the ones we've considered so far. the rate increases with a better leaving group, right? The first thing that happens is my leaving group leaves. So if it likes to leave more, it's going to be a faster rate. The solvent. My solvent for this one, we are going to prefer polar protic solvents. And then the substrate, which is our alkyl halide in this case. Because we are going through that carbocation intermediate, we want the more stable intermediate. So tertiary is going to be better than secondary, which is going to be better than primary. The only mechanism that we've seen so far where this trend was the opposite was SN2. So if you have something that's a primary alkyl halide, SN2 is a really good place to start as far as considering what it's going to, or how it's going to react. These ones, again, they also like allylic and benzylic are also good. Right, remember these guys have resonance. And then I know I've said this a couple times, but the rate law, right, my rate determining step for E1 and SN1 are the same. So both of them go through the same exact intermediate. So then what happens is just sometimes a nucleophile adds to that carbocation. Sometimes a proton is taken by a base. It doesn't even have to be a strong base. And then we form that pi bond. So often E1 and SN1 reactions compete. So E1 and SN1 reactions often compete, meaning often we get both products. Right? They have the same first step. Rate law. Intermediate. So often we'll get a mixture of products. We'll get both the substituted and the eliminated product. So we will make a table where we kind of compare and contrast E1 and E2 like we did with the SN1 and SN2 reactions. But I do want to talk about elimination of halocycloalkanes real quickly. These ones undergo a specific sort of geometry. So elimination of halo. So there's a halogen on them, cycloalkanes. And specifically cyclohexanes, let's actually just write it that way. So elimination of halocyclohexanes. So remember, a cyclohexane is going to adopt that non-planar chair conformation. So that's going to give us specific geometry for how they eliminate. So for E2, for E1, it's not going to matter because it's not concerted. You're going to go through a carbocation. But here, because the leaving group is leaving at the same time that we're taking that proton and forming the pi bond, the geometry does matter. Remember that it needed to proceed through that anti-coplanar or anti-periplanar geometry. If I have a chair conformation, now it becomes even more specific. So for E2, the carbon-halogen bond, so the leaving group, right, the carbon and the leaving group must be anti-periplanar or anti-coplanar to the carbon-hydrogen bond on the beta carbon. I don't think I've used that term before, alpha and beta, but alpha carbon is always the carbon that we're talking about. So if I'm talking about an alkyl halide, the carbon that the halogen is attached to is my alpha carbon. And then the carbon next door to that is my beta carbon. So this is true for all E2 mechanisms, right? When we say they have to go anti-periplanar, anti-coplanar, we're saying that the halogen and the hydrogen have to be anti to each other, and they have to be on adjacent carbons. So if this was my carbon, right, or my substrate, this carbon right here is my alpha carbon. It's always the one that we care about. So if it's an alkyl halide, the carbon the halogen's attached to is my alpha carbon. If I was talking about an alcohol, then the carbon that the hydroxyl group attached to would be my alpha carbon. And then one carbon away is the beta carbon. So this is a beta carbon. This is also a beta carbon. So when we eliminate, we're actually taking the hydrogen from the beta carbon, right? So I could end up with this alkene. That would be my major product. That's taking it from that beta carbon. Or we could end up with that alkene. That would be my minor product, right? It's less substituted, but it's still a possible product because we're taking a hydrogen from a beta carbon. And again, this isn't specific to halocyclohexanes. This is just specific to E2 reactions in general. Basically, our dehydrohalogenation reactions, the hydrogen is on the beta carbon. I just hadn't used that terminology in the past. So for E2, the carbon-halogen bond must be anti-periplanar to the carbon-hydrogen bond on the beta carbon. Worded differently, but old news. For cyclohexanes, remember these guys are in chair conformations, so we have axial and equatorial positions. This must occur with trans. It's the only way we're going to make them antis if they're trans. And then they both need to be axial, so diaxial geometry. This actually can have an effect on the regio specificity of it. We might not actually get the more substituted product anymore. It just might not be possible because it has to be trans diaxial. So this may affect the regiochemistry. By regiochemistry, I just mean it may affect what region, right, where part of the molecule we're taking that hydrogen from. So an example for us. So an example, let's say we have this chair. And I'm going to put my chlorine going up in that axial position, and then I have a methyl group in this equatorial position. Be careful, because I would totally do this to you. I think you guys know me well enough by now to know that this is totally in the realm of possibility. Also that I'm not very good at drawing them from this way. So this molecule that I drew above, right, if I was to do a chair flip, right, a ring flip with it, my chlorine is here, and then this group is here. I could very, very, very possibly give you this to start. If I give you this to start, you need to do a chair flip to draw the one above because my chlorine needs to be axial to eliminate, right? If we go up here, transaxial geometry, right? What that means is the halogen must, M-U-S-T, all capital, be axial to eliminate. If it's equatorial, like it is in the one that I have in the box here, you need to do a chair flip, right? It needs to be a ring flip to put it in the axial position, right? Remember, when you do your chair flip, if it was equatorial, it becomes axial and vice versa. So if I give it to you equatorial, then you have to do a chair flip, otherwise you're not going to be able to eliminate it. So the halogen must, we'll underline it a few more times, be axial to eliminate. If given a molecule where the halogen is equatorial, you must do a chair flip, ring flip, whatever you want to call it, first. You don't have an option. I guess you do have an option. You could do it wrong, but you would lose points. So if you want to do it correctly, the halogen needs to be axial. It cannot eliminate from the equatorial position. So if it's equatorial, then you have to do a chair flip first. So again, if I gave you this, the first thing you need to do is do your chair flip so it looks like the molecule above. Once it's in that position, then I can do my elimination. I'm going to draw my hydrogens on here. I'm going to look at my beta carbons, and I have two of them, right? I have one here. It's one carbon. Oop, I drew alpha. It's one carbon away from my alpha carbon. That's alpha. So I have beta here, and I have beta here. The hydrogen needs to be anti to it, and it also needs to be axial. So on this carbon, because axial on my alpha carbon is up, axial on this carbon is down, so I do have a hydrogen going down. And then on my other beta carbon, because my methyl group is equatorial, I also have an axial position bonded to that hydrogen. So I actually have two options for this one when we eliminate. I can end up with my double bond here, and I can end up, what's that methyl group, with my double bond here. That's kind of hard to see. My double bond here. There's still that methyl group there. Both of those are possible, right? If we go back and look again, this and this are trans diaxial. So I can take this hydrogen, and that would give me this second product, which is actually my minor product, right? It's di-substituted. Or I could take this purple bond, right? That hydrogen and chlorine, right? Those are both purple now. This would be my major. It is tri-substituted. So we would get both of those products are possible. Another example for us . And again, I'm starting out with the chlorine axial. If it wasn't axial, you would need to do a chair flip to get it axial. And then this time on that carbon, I'm going to put that methyl group. So when I look at my possibilities for hydrogens that I can eliminate, I still have this one here, that's axial. But in the axial position on this carbon, right, in this carbon, my methyl group is axial, which means my hydrogen is equatorial. So because this hydrogen is equatorial, that is not an option for elimination, right? They both have to be axial, right? Trans diaxial, di meaning two, both of them are axial. So my only possible product for this one when we eliminate is this one. Only the di-substituted product. right? If it was planar, if I wasn't considering chair conformation in the axial equatorial positions, then you could draw the tri-substituted product, right? There is a beta hydrogen there, but that beta hydrogen is equatorial because the methyl group is axial. The hydrogen and the halogen that you eliminate have to both be axial. So this time only the one product.